Well, hi everyone. Thanks so much for being available and minds on to take a look at some new topics. Today, our main topic, excellent haircut. Today, our main topic is to be able to recognize an exponential function from a graph, a table, or an equation. Any of the three forms, you should be able to look at it and say, I know that's linear, I know that's quadratic, I know that's exponential, depending on what it is. So let's take a look. If we're looking at an equation, these are the simplest ones to identify. I would probably say, if you're looking at a linear equation, you're going to see something that looks like a y equals mx plus b is one form that you might find, or y equals some number multiplied by x. This is still an y equals mx plus b here. B just happens to be 0 in that case. Or you'll see it in ax plus by equals c. These can be rearranged to y equals mx plus b, but all of them have an x with an exponent of 1. Of course, we don't ever show that exponent, because that would be like saying I'm 42 to the 1 years old. You're just about all of you 16 to the 1 years old? Or 15 to the 1, 16 to the 1. Yeah, just about all 16 to the 1 years old, yeah. Okay. All right. Which is another way of saying 2 to the 4 years old, or 4 to the 2. Quadratic equations, of course, you're going to recognize them by seeing an x squared somewhere in the equation. Even if they're not in standard form like this, we can still recognize that that's a quadratic. Also, algebra that creates x squareds, like x plus 1 multiplied by x plus 2, that will still be quadratic, because when I use FOIL, the x times the x creates the x squared term. And so that's how you would recognize a quadratic. You see an x squared. Or you see that it would be making an x squared if you expand it. The last one, if it's exponential, yeah, you're going to see the variable as the exponent. You're going to see it in some way like that. Okay? It could be a transformed version. These all have various transformations applied to them. But when that x is when the variable is up in the exponent, then you have an exponential function. Now, this says it has an x as the exponent. We often see t as time. So we'll often have t instead of x. Many of our exponential functions have time as the variable. Many things are growing or decaying exponentially through time, and so time is very frequently that what we will label the independent variable as. Let's keep going. Okay, take down some of these ideas, and then we shall continue. Allie?
How does x have the exponent of 1 on the last one, like 2x?
Oh, here? Oh, this is 2x raised to the power 1. And if I rearrange that one, I'm just going to scroll a little bit. I would, if I wanted to show you that one in y equals mx plus b form, I would get out my inverse operations pen, subtract 2x from both sides. Here's a tip, and I see that when I was going through the Unit 2 tests, I noticed that some of you would benefit from this tip. When you're doing your inverse operations to isolate different variables, in this case I want to isolate y, try them in inverse Bedmas order. First, deal with any loose addition and subtraction. You can move those very easily from one side of the equation to the other prior to working on multiplication and division, prior to working on exponents, prior to working on stuff inside the brackets. So first I move that 2x because it's being added to 3y, and then I'm going to divide away that 3. So first do the addition and subtraction, and then do the multiplication and division. So that would be, I'm going to write it over here. Y is equal to negative 2 over 3x plus 2, because 6 over 3 is just 2. So there you go, that's just a y equals mx plus b. And that's going from, we actually call this standard form of the line, ax plus b y equals c. I don't know why it's standard form. I very rarely, we often just want to convert to y equals mx plus b. That's kind of our standard. But this one's called standard form for the line. Carry on now? Let's go. All right, so let's take a look at these examples. Tell me, is A, what kind of equation is that? Linear, quadratic, or exponential? Yeah, okay, I see the x as the variable is the exponent. Great, that's exponential. 7x squared plus 5y minus 2. Oh yeah, that's a quadratic, has a stretch factor of 7, has a y-intercept of minus 2. It's crossing the y-axis and rising, so it looks something like this. And because it has a stretch factor 7, it's opening upwards, and it's very stretchy. It looks something like that. 9x plus 3 equals y. What's that? This is linear. That has a y-intercept of plus 3 and a slope of 9, so it's doing something like this. If I asked you to find the intersection between these two things, you'd find two of them. You'd find one up here and one down there. And then this, what is that? Linear, quadratic, or exponential? But there's a 2 up there. Why is that still exponential? Because reasons. Yeah, because that's just a transformation, Mr. Jennings. That's just like a k value. This x is your main variable. That's an exponential function. There we go. All right. So now let's take a look at how we identify them from a graph. Well, linear ones make a straight line. Quadratic ones have a u or a upside down u. And exponential ones rise or fall quickly in one direction, but only in one direction. They don't rise on both sides the way a parabola does. Like parabolas, they're curves. But unlike parabolas, we'll see that the way they curve is a little different. And we're going to take a look at that more when we look at point by point. So I'll let you get this down for just a second while I prepare the next interactive activity. Okay, let's go. All right, so let's take a look at this mini activity here where we're going to graph together f of x equals x, g of x equals x squared, and h of x equals 2 to the x. It'd be nice to have 3 different examples side by side so we can see how they look different. So if you have different colors, that might be useful, or different highlighters to highlight each one. That would be great. Otherwise, you could use dashed lines, dotted lines, etc. to distinguish, but you'll be able to tell. Anyone need a table of values for f of x equals x? I'll make one real quick. Okay, so we're going to be looking at values from, I'd say we want to look at from -2 to 4. So here, if we look at x value and then f of x value, that's -2, -2. 0 is 0, 2 goes to 2, and 4 goes to 4. Okay, let's make a quick little table of values. Ha, just a little math joke there. Okay, y equals x, that's what it looks like. And then you graph it. So this is always available to you. Just make a quick table of values. I'm kind of joking because this one is just the line y equals x, so it's pretty simple. But, you know, take what we do when things are simple and apply it when things are complex, and it will help you out quite a lot. So that's the line y equals x. So maybe I label that f of x here. Cool. Now, how about g of x equals x squared? Let's make a table of values. Well, I notice that my range here from my graph paper is up to 4. So that gives me a hint as to what x values I could look at. So if I look at x values here and outputs for g of x, which is just x squared, then I could look at -2 goes to 4, 1 goes to 1, 0 goes to 0, 1 goes to 1, -1 also goes to 1, and 2 goes to 4. There's my table of values. Plot it. So we have an intersection. I'm just going to circle that because it's kind of cool. There's an intersection there. Oh, there's another intersection there. And then I'm going to put these points on. Boop, boop. Okay, and then boop again. Cool. And now, I think it's cool. Maybe you don't. Graph it. There. G of x. And the last one, h of x equals 2 to the x. if we look at the same x values, well, we could look all the way down to -4. There's nothing stopping us looking at -4 here. 2 to the x. So let's look at -4. We'll look at -1. We'll definitely look at x is equal to 0. And we'll look at 1 and 2. I could have looked at -2 over there and then just kind of guessed what -4 was going to look like. Let's start in the middle. 2 to the 0, what's that? Starting here. It is 1. Why is it 1? How can I have a quick way of remembering that something to the 0 is 1?
It's just like a rule that whatever is like to the power of 0 is 1.
Everything to the power 0 is 1. And when you look at a graph, you're going to see that that creates a smooth curve from your negative values to your positive values. If you make the very common, and I will reinforce here, the very common student error, and sometimes I might make this error too, that something to the 0 is equal to 0, you'll notice that your graph is not a smooth curve. You have something that's not in the right place because it's incorrect. So let's get that one right. So 2 to the -1, what's that? It is 1/2. The role of that -1 exponent, let's look at it, 2 to the -1 is equal to 1 over 2 to the 1. The negative exponent just kicks the base to the bottom of the fraction. So, by that logic, what's 2 to the -4? Hmm? 2 to the -4. 1/16 is correct. So, again, the common student error will be to say, well, it's 2 to the 4, but negative, like it's -16. No. Now, the negative exponent does not change the positivity negativity of your base. It just pushes it to the bottom of the fraction. And so then that's the same thing as saying 1 over 2 to the 4. 2 multiplied by itself 4 times is 16. So that gives us 1 over 16. 2 to the 1, it's just 2. How about 2 to the 2? 4. Good. Okay, so let's plot these points. Let's start in the middle. To the 0, well, that was 1. And then to the -1, well, that was 1/2. So 1/2 I would plot there. Notice that's 1/2 the way to 1. 2 to the -2, you can do this in your head. It's 1/4. To the -3, it's 1/8. And to the -4, it's 1/16. And when I'm that tiny on my graph, I'm no longer interested in how exact I can get. I'm just showing the shape, and it's generally approaching 0 in that direction. It will never become 0. It will always be 1 over 2 to the something. Even when to the something becomes very big, you will still be very close to 0, but not exactly 0. Allie?
Can you go over how you found those points?
Which the ones I just did?
Yeah.
I did the math in my head. So 2 to the -3 would be 1 over 2 to the 3 is 1 over 8. 2 to the -2 is 1 over 2 to the 2 is 1 over 4. We calculated that one, and these ones follow the same pattern in between. Each one is half again as big as the one bigger than it. So it always grows by a factor 2. Over here to the 1, we had the point 1, 2, and then 2 to the 4 is an intersection. I'm going to circle it. There's an intersection there. Now we can do a smooth curve going through here, growing, and eventually deciding to blow up. Like that. So that's what our graphs will look like. H of x. So what else to say about that? I don't know. Do you need to have anyone have any questions here? No? Okay, let's get back to the presentation. So we've seen that when we had the y equals x squared, we had the u, y equals x, it's a straight line, and then y equals 2 to the x, that's smoothly rising until it suddenly starts rising very quickly. Let's keep going. Now looking at tables, this is where we're going to get some practice today during the presentation, and where we're going to also review linear, quadratic, and exponentials. So if you recall, looking at a linear function, the first difference has to be constant for a linear function. For quadratics, when we look at it, the first difference is always going to be varying, but the second differences will be constant. If we apply first or second differences to exponentials, we'll find that doesn't lead us to a better understanding of them, because they're not growing in an addition type of way, they grow through multiplication. It's fundamentally different, the way that it curves and the way that it grows.
Are there examples for each of them?
Yeah, and we're going to take a look at some examples. Do I have some examples on your sheet? Yeah, we're going to do those examples together. So let's take a look at some tables. Huh? That was a hold on a second? Yeah, okay, good. All right. Let me answer Ali's question with a little more detail while you're doing that. So one thing that I really like about graphing exponential functions is it's great mental math practice. If I have something like 2 to the x, and I want to know its values at like -6, -5, -4, -3, -2, -1, let's say, for x, and then I'm looking at what's the value of 2 to the x. Here, this is 2 to the -6, which is equal to 1 over 2 to the 6, which is equal to 1 over 64. So this is how I get these out. 2 to the -5 equals 1 over 32. 2 to the -4, 1 over 16, 1 over 8, 1 over 4, 1 over 2. They're just right there. They're all in there. Let's go. Let's take a look at some tables. All right. So if we apply our analysis skills on tables here I would notice that my first difference, this grows by 4 to go from 5 to 9. To go from 9 to 13, it grows by 4 again. To go from 13 to 17, it grows by 4. And to grow from 17 to 21, it grows by 4. What kind of equation do I have here? This is linear. This is actually the line y equals 4x plus 1. And I can tell because the first difference is 4, so the slope is 4, and its y-intercept, I can tell if I walk back from x to 0, that would be 1. So that's how I know that it's 4x plus 1. Let's take a look at this one. Here, it got smaller by 1, and then it got bigger by 1. Then it got bigger by 3. Then it got bigger by 5. What are we looking at? How do you know it's a quadratic, Oscar? These aren't all the same. Yeah. Yeah. Yeah, that's a step pattern for a quadratic with an a value of 1, isn't it? So here we look at second differences. -1 grows to 1. That's an increase of 2. 1 grows to 3. That's an increase of 2. 3 grows to 5. That's an increase of 2. So yes, this is indeed, because we see second differences are constant, this is quadratic. See ya, Creedy. And then finally, this one, let's see how it grows. 3 grows to 9. Well, that increased by 6. 9 grew to 27. That increased by 18. 27 growing to 81. That increases by 54. And 81 growing to 243. Well, that increased by 162. So notice that if I then do second differences, I'm not going to see a constant pattern. It's growing by 12. It's growing by, well, what is that there? Something bigger than 12. And then growing by, again, something bigger than 12 if I do second differences. But what I can notice, yeah, they all have factor 3. And in fact, this is multiply 6 by 3 gets 18. Multiply 18 by 3 gets 54. Multiply 54 by 3 gets 162. Yeah.
Could you just do that in the first place without 6, 18, 54, 162?
Yep. You could. And you would find that this is multiplied by 3. 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 And if I do the second differences, I'll still get them multiplying by 3. Let's test. 6 to 18 grew by 12. Does 18 growing to 54 grow by 36? Well, it does. Plus 36. 54 growing to 62. Well, that grows by 108, right? Yeah, 108. So even if I do second differences, I still have that multiplication pattern in between the numbers. So when you see things growing by multiplication, not by some kind of addition, and there with a quadratic, the addition is buried in the second level, but you can still see it's just adding. This is an exponential function, yeah. That one's quadratic. Oh, that one's linear. Yeah, that one's y equals 4x plus 1, that's linear. This one's quadratic. So one time I don't want to do too many stories, but yeah, that's growing exponentially. So let's take a look at this one. What kind of function am I looking at here? No, we haven't seen this one, didn't we? Oh, we did see this one. Yes. Oh, yeah, these are all the same. Yeah, okay. So next, what we have to look at is some practice questions that you can take a look at in your package. And they are down here. Taking a look at these equations, tell me if they're linear, quadratic, or exponential. Take a look at these tables, tell me if they're linear, quadratic, or exponential. And then take a look at these graphs, tell me if they're linear, quadratic, or exponential. Go ahead and work on those and ask me questions about those while I'm handing back your tests and coming to chat with you about your tests. At the end of the period, we'll go over a brief review that we'll use for the quiz tomorrow.